Look up at the night sky on a clear evening, and you'll see a vast ocean of stars, galaxies, and cosmic wonders. But here's the shocking truth. Everything you can observe with your eyes, even through the most powerful telescopes, makes up less than 5% of the universe. The rest, an invisible, mysterious realm dominated by forces we barely understand, dark matter and dark energy. Imagine the universe as a grand puzzle, and we've only just begun to piece together the edges while the center remains hidden in shadow. Galaxies spin faster than they should, the cosmos expands at an accelerating rate, and scientists are still scrambling to explain why. It's like walking into a room, seeing furniture floating midair, and realizing there's an invisible elephant no one told you about, except this elephant makes up 27% of everything that exists. What if I told you that the stars and planets we cherish are just the glitter on the surface of something far stranger? Dark matter's gravitational pull holds galaxies together like cosmic glue, while dark energy pushes the universe apart with an unstoppable force. These hidden players dictate the fate of everything, yet we can't see them, touch them, or even fully comprehend them. It's one of science's greatest detective stories, filled with twists, dead ends, and breathtaking revelations. From ghostly particles that pass through you unnoticed to a repulsive energy stretching space itself, the deeper we dig, the more questions we uncover. That's where this journey begins. Over the next few minutes, we'll explore 25 mind-blowing facts about these cosmic enigmas, facts that will challenge how you see the universe. Why do galaxies defy the laws of physics? How could dark energy tear reality apart in the distant future? And what if everything we think we know about the cosmos is just the tip of an iceberg lurking in the dark? Strap in, because we're about to dive into the invisible forces that shape existence itself, and by the end, you'll never look at the night sky the same way again. Back in 1933, a Swiss astronomer named Fritz Zwicky was studying a cluster of galaxies called the Coma Cluster when he stumbled upon something bizarre. The galaxies were moving so fast that, by all calculations, they should have flown apart, yet they stayed tightly bound together. The gravity needed to keep them in place was far stronger than anything the visible stars and gas could produce. It was as if invisible hands were gripping the cluster, refusing to let go. Zwicky called this mystery substance Dunkel Materie, dark matter, and though his peers dismissed it at the time, he'd just cracked open one of cosmology's greatest puzzles. Think of dark matter like the wind. You can't see it, but you know it's there when tree branches sway or leaves scatter. It doesn't glow, cast shadows, or interact with light in any way. The only reason we know it exists is because its gravity tugs on stars and galaxies, warping their paths like an unseen puppeteer. Without dark matter's invisible scaffolding, galaxies would spin themselves apart, their outer stars flung into the void. Our own Milky Way is wrapped in a halo of this ghostly material, its gravitational embrace keeping everything from the solar system to distant star clusters in check. Here's what makes it even stranger. Dark matter isn't just hiding in the corners of space, it's everywhere, passing through you right now. Trillions of particles could be streaming through your body every second, leaving no trace. It's as if we're living in a house filled with silent roommates, their presence revealed only when furniture mysteriously moves. Scientists have spent decades trying to catch these elusive particles in underground labs, shielded from cosmic interference, but so far, dark matter remains a cosmic whisper, felt but never seen. And yet, without it, the universe as we know it wouldn't exist. Picture the universe not as a random scatter of galaxies, but as an intricate spiderweb stretching billions of light years across, an invisible architecture woven from dark matter. This cosmic web is the skeleton of existence, its ghostly filaments threading through the void, guiding galaxies into place like beads on a string. Simulations reveal a breathtaking truth. Where these dark tendrils intersect, galaxies flock together in glowing knots while the spaces between, the voids, remain eerily empty, some so vast they could swallow thousands of Milky Ways without a trace. It all begins with dark matter's gravitational pull. After the Big Bang, while ordinary matter was still a chaotic soup of particles, dark matter began clumping together, forming a scaffold of dense knots connected by wispy threads. Over billions of years, normal matter gas, dust, stars, was drawn like iron filings to a magnet, sliding along these invisible highways to form the galaxies we see today. The result, a universe structured like a sponge, with glittering cities of galaxies strung along dark matter's filaments and yawning deserts of nothingness in between. Those voids tell their own chilling story. Imagine floating in one, a region so empty the nearest galaxy might be tens of millions of light years away. The darkness would be absolute, not just from the lack of stars, but because these voids are still expanding, stretched even wider by dark energy's relentless push. Meanwhile, along the web's bustling filaments, galaxies collide, merge, and ignite with new stars, all orchestrated by the unseen hand of dark matter. Here's the twist: without this hidden scaffolding, our night sky would look utterly different. Galaxies wouldn't cluster into superclusters, they'd drift apart like lonely ships in an endless ocean. Even the Milky Way owes its place in the cosmic neighborhood to these invisible threads, just one city among millions in a dark matter metropolis spanning the observable universe. And just like a spiderweb trembles when touched, astronomers can map this hidden structure by watching how galaxies move within it, their paths bending under the weight of something we still can't see. One of the most persistent myths about dark matter is the idea that it could simply be an army of black holes lurking in the cosmic shadows. After all, black holes are invisible, incredibly massive, and exert tremendous gravitational pull. So why wouldn't they fit the bill? But the universe has a way of leaving clues, and when scientists went hunting for proof, the evidence pointed in a completely different direction. Take gravitational lensing, for example. When a massive object like a black hole passes in front of a distant star or galaxy, its gravity bends the light around it, creating a magnifying effect that astronomers can detect. If dark matter were made of black holes, we'd see these lensing events constantly, tiny flashes and distortions scattered across the sky like cosmic breadcrumbs. Yet after decades of searching, the numbers don't add up. There simply aren't enough of these lensing events to account for the staggering amount of dark matter needed to hold galaxies together. It's like searching for a herd of elephants in a field and finding only a few scattered footprints. The scale is all wrong. Then there's the Planck satellite, which mapped the faint afterglow of the Big Bang with unprecedented precision. Its observations placed strict limits on how much of the universe could be made of primordial black holes, the hypothetical remnants of the early cosmos. The verdict: even if every single one existed, they'd contribute only a tiny fraction of the dark matter we know is out there. So if it's not black holes, what is dark matter? The leading theory points to something far more exotic: an undiscovered particle that barely interacts with ordinary matter at all. Imagine a universe teeming with invisible guests, passing through walls, planets, even you, without so much as a whisper. These hypothetical particles, whether WIMP, actions, or something entirely unexpected, would form vast, diffuse halos around galaxies, their gravity sculpting the cosmos without ever revealing themselves directly. The hunt for these particles is one of science's greatest challenges. Deep underground, detectors wait in silence, hoping to catch the rare moment a dark matter particle bumps into an atom. In space, telescopes scan for unusual gamma rays or other traces of these phantoms decaying. Every null result, every dead end, brings us closer to the truth, because in science, knowing where not to look is just as important as knowing where to look next. Black holes may be the universe's ultimate ghosts, but dark matter is something else entirely, a shadow puzzle we're still learning how to solve. and until we crack it, the cosmos keeps its deepest secrets hidden in plain sight. Our Milky Way isn't just a swirling disk of stars and gas, it's a cosmic island floating in an ocean of invisible matter, a vast halo stretching hundreds of thousands of light years into the void. This ghostly envelope, made entirely of dark matter, dwarfs the visible galaxy, containing up to 10 times more mass than all the stars, planets, and dust combined. Picture it like a lighthouse surrounded by fog. We see the beam, but the true scale of the fog remains hidden, its presence only revealed by the way it bends and distorts everything around it. Thanks to the Gaia spacecraft, a revolutionary mission mapping the positions and motions of over 1 billion stars, we've glimpsed this halo's gravitational fingerprint in stunning detail. Gaia's data shows stars on the Milky Way's outskirts whipping around far faster than they should if only visible matter were pulling them. It's as if the galaxy's outer stars are cars speeding down a highway with an unseen force pressing down on the accelerator, keeping them from flying off into intergalactic space. This mismatch between what we see and how things move is the smoking gun for dark matter's overwhelming influence. The halo's shape is another puzzle. Unlike the orderly spiral of the Milky Way's disk, simulations suggest the dark matter halo is lumpy and asymmetric, more like a tangled cloud than a perfect sphere. Some regions may be denser, acting like hidden anchors that subtly tug stars off course. Even stranger, the halo might be slightly squashed, flattened by the galaxy's rotation in ways we're still trying to measure. This invisible structure doesn't just hold the Milky Way together, it shapes its very evolution. When smaller galaxies drift too close, the halo's gravity shreds them into streams of stars, wrapping them around our galaxy like cosmic ribbons. The remnants of these ancient collisions, visible as faint stellar currents in the night sky, are clues to the halo's past. And because dark matter doesn't collide or slow down like normal matter, it provides a stable skeleton, preventing the Milky Way's spiral arms from unraveling over billions of years. Yet for all its power, the halo remains frustratingly elusive. Unlike gas or stars, dark matter leaves no thermal fingerprints, no radio whispers. Its presence is written solely in the silent choreography of orbiting stars and the subtle warping of space-time. Some theories suggest the halo could harbor dense clumps or even exotic structures like dark matter, rivers, currents flowing through the galaxy's veins. Others propose it might interact faintly with itself, creating invisible sparks we've yet to detect. One thing is certain, without this hidden anchor, the Milky Way as we know it wouldn't exist. The delicate balance of gravity and motion that keeps stars in their orbits, that guides entire galaxies through the cosmic web, depends on the ghostly embrace of dark matter. And as Gaia and future telescopes peer deeper into the halo's secrets, we're not just studying our galaxy's hidden architecture, we're uncovering the rules of an invisible universe, one star's motion at a time. For centuries, scientists assumed the universe's expansion was slowing down, like a ball thrown upward, gradually losing speed to gravity's pull. Then, in 1998, two separate teams of astronomers made a discovery so startling it turned cosmology upside down, winning them the Nobel Prize. By studying distant supernovae, these researchers found that the universe wasn't just expanding, it was accelerating, as if some invisible force was pressing harder on the cosmic gas pedal with every passing moment. The implications were staggering. Either Einstein's theory of gravity was fundamentally flawed, or a mysterious, repulsive energy was flooding empty space, pushing galaxies apart faster and faster. That energy, dubbed dark energy, now accounts for a jaw-dropping 68% of the universe's total content. Imagine blowing up a balloon with tiny dots on its surface. If you inflate it slowly, the dots drift apart predictably. But if you suddenly pump air in faster, the dots accelerate away from each other. That's the universe under dark energy's influence. What makes this even stranger is that unlike gravity, which weakens with distance. Dark energy's push grows stronger as space expands, creating a runaway effect that could one day tear galaxies apart atom by atom. The leading explanation: vacuum energy, a property of empty space itself. Quantum theory suggests that even a perfect vacuum isn't truly empty but seethes with fleeting particles popping in and out of existence. These quantum fluctuations might generate a tiny repulsive force per cubic centimeter, but when added up across the cosmos, the effect becomes colossal. Einstein actually predicted something similar with his cosmological constant, a term he once called his greatest blunder, but now might be the key to understanding dark energy. Yet mysteries remain. If vacuum energy is so powerful, why doesn't it rip atoms apart locally? Why does its strength match the critical density needed for cosmic expansion so precisely? Some theories suggest dark energy isn't constant at all but evolves over time, perhaps tied to undiscovered fields or dimensions. Others propose it's a sign we're missing a deeper layer of physics altogether. One thing is certain: dark energy's discovery reshaped our cosmic destiny. Without it, the universe might have collapsed back in a big crunch. Instead, we're hurtling toward a colder, lonelier fate. A big freeze where galaxies vanish over the horizon, leaving civilizations of the future with a sky nearly empty of stars. And as telescopes like the Vera Rubin Observatory peer deeper into this puzzle, each new measurement brings us closer to understanding the force that will ultimately decide everything's fate. If you took the entire universe and compressed it into a single pie chart, the slices would tell a humbling story. The biggest piece, a whopping 68%, belongs to dark energy, that mysterious force accelerating the expansion of space itself. The next largest, 27%, is dark matter, the invisible glue holding galaxies together, and that tiny sliver left over, just 5%. That's everything we can actually see: stars, planets, nebulae, and every living thing in existence. To put that in perspective, imagine standing in a vast, foggy field at night. You're holding a flickering candle, its tiny flame illuminating just a few feet around you. That's the visible universe, the stars, galaxies, and cosmic wonders we've catalogued. But beyond that dim circle, stretching endlessly in every direction, is an ocean of darkness teeming with forces we can't perceive. Scientists call this the cosmic embarrassment, the glaring fact that 95% of reality is made of stuff we literally don't understand. Here's what makes this cosmic budget even wilder: that 5% isn't evenly distributed. Most of it isn't even solid matter like planets or people. It's hot gas floating between galaxies in threads so diffuse you'd barely notice them. The atoms forming your body, the screen you're watching this on, even Earth itself, are cosmic rare treasures, in a universe dominated by darkness, we're the exception, not the rule. This imbalance reshapes how we think about existence. Dark energy's overwhelming majority means it calls the shots on the universe's fate, stretching space faster while galaxies fight to hold themselves together against the tide. Dark matter, though less abundant, acts as the cosmic architect, sculpting the large-scale structure of everything. And ordinary matter, it's just along for the ride, clumping where dark matter's gravity allows, forming the glittering islands we call galaxies. The irony is brutal. After centuries of studying the heavens, peering deeper into space than ever before, we've realized we're barely scratching the surface. It's like finally deciphering an ancient book only to discover 95% of its pages are written in ink we can't see. Every telescope, every probe, every experiment is now racing to read those invisible words, because hidden within them are the answers to where the universe came from and where it's headed next. Dark matter doesn't just hide in the shadows, it's cold. Not in the icy void of space kind of way, but in the sense that its particles move sluggishly, lumbering through the cosmos like giants wading through molasses. This cold dark matter model is the leading explanation for how our universe's structure emerged from the chaos of the Big Bang. Imagine tossing a handful of sand into a still pond. The heaviest grains sink fastest, forming dense clumps at the bottom, while finer particles drift slowly, settling into a delicate web. Cold, dark matter behaves like those heavy grains, collapsing early under gravity's pull, creating gravitational wells that ordinary matter, the gas and dust that would become galaxies, could later slide into. The alternative, picture hot, dark matter, made up of particles zipping around at near light speed like neutrinos. These speedy particles would have washed out small-scale structures, preventing galaxies from forming until much later in cosmic history. The universe would look eerily different, a sparse soup of massive supergalaxies with none of the intricate diversity we see today. Warm dark matter, a middle ground theory, suggests particles moving just fast enough to smooth out some small structures, leaving behind a cosmic landscape missing the tiniest dwarf galaxies. But observations tell a different story. The universe is lumpy in exactly the way cold dark matter predicts, with galaxies of all sizes nestled inside vast halos of this slow-moving stuff. Here's where it gets fascinating. Cold dark matter's sluggishness isn't just a quirk, it's the reason galaxies exist at all. In the early universe, tiny ripples in dark matter's distribution acted like cosmic seeds. Gravity amplified these ripples, pulling more dark matter into dense knots. Over billions of years, these knots grew hierarchically, merging like droplets of water on a window pane, building up from tiny clumps to massive galaxy clusters. Without cold dark matter's patient, lumbering nature, that growth would have been chaotic, like trying to build a sandcastle in a hurricane. The evidence is etched into the sky. Computer simulations of cold dark matter produce virtual universes eerily similar to our own, complete with twisting spiral galaxies, sprawling clusters, and delicate filaments, all emerging naturally from the physics of slow, heavy particles. Even the Milky Way satellites, tiny dwarf galaxies orbiting like fireflies, match predictions. Warm or hot dark matter would have erased these fragile structures, leaving behind a universe far smoother, far emptier. Yet the mystery isn't fully solved. Some discrepancies linger, like the missing satellites problem simulations predict more dwarf galaxies around the Milky Way than we've found. Others point to galactic cores less dense than cold dark matter suggests. These wrinkles hint that dark matter might be more complex than we think, perhaps with a sprinkle of warmth or unexpected interactions. But for now, the cold dark matter model remains the universe's best-fitting puzzle piece, the invisible hand that shaped everything from the grandest galaxy to the faintest star. And every new observation, every deeper simulation, brings us closer to understanding the slow, silent dance that built the cosmos. One of the most dramatic pieces of evidence for dark matter comes from a cosmic collision so violent it ripped the fabric of a galaxy cluster apart and left its secrets exposed. 2 billion light-years away, two massive clusters known collectively as the Bullet Cluster slammed into each other at speeds of millions of miles per hour. The impact was so powerful it wrenched normal matter, the hot gas between galaxies, away from the unseen mass holding everything together. The result, a cosmic crime scene where dark matter literally left its fingerprints. Here's how it happened. When these clusters collided, their galaxies, made of stars and dark matter, passed through each other like ghosts, barely affected. But the superheated gas between them, that couldn't slip past so easily. Like two clouds of smoke hitting head-on, the gas particles smashed together, slowing down and piling up in the center. Meanwhile, the dark matter, unaffected by friction or electromagnetic forces, kept racing ahead, carrying the galaxies with it. This left a bizarre separation. Most of the cluster's visible mass stuck in the middle, while the bulk of its gravity, traced by distorted background galaxies, lurked on either side. Scientists mapped this using gravitational lensing, nature's magnifying glass. Dark matter's gravity warps spacetime, bending the light from galaxies behind it like a funhouse mirror. By analyzing these distortions, researchers could pinpoint where the mass was concentrated. The verdict: the bullet cluster's gravity didn't align with its glowing gas at all. It was as if a car crashed and the passengers walked away unharmed while the seats tumbled in the opposite direction. This wasn't just a quirky observation, it was a smoking gun. Alternative theories like modified gravity couldn't explain the separation. Only dark matter, with its ability to pass through itself, and ordinary matter like a phantom, fit the data. The bullet cluster became the gold standard, proving dark matter wasn't just a mathematical fix, it was real, physical, and shaping the cosmos in ways we could finally see. But the story doesn't end there. Other merging clusters like Max J0025 show similar separations. Some even reveal dark matter clumps with no visible galaxies at all, ghostly islands floating in the cosmic web. Each collision peels back another layer of the mystery, showing us a universe where the invisible outweighs the visible and where the most fundamental forces remain just out of sight. The bullet cluster didn't just prove dark matter exists, it gave us a front-row seat to the hidden mechanics of the universe. Gravity has always been the universe's great gatherer, pulling planets into orbits, sculpting galaxies, and drawing clusters together over billions of years, until dark energy flipped the script. Unlike dark matter's relentless tug, dark energy behaves like a cosmic repellent, stretching space-time itself apart with a force that grows stronger as the universe expands. Imagine two magnets. Dark matter pulls them together, while dark energy actively pushes them apart, not just resisting gravity but overpowering it on the largest scales. This bizarre anti-gravity effect traces back to an idea Einstein once tossed aside. In 1917, struggling to reconcile his equations with a static universe, he introduced the cosmological constant, a mathematical fudge factor representing a repulsive force balancing gravity. When Edwin Hubble later proved the universe was expanding, Einstein called it his biggest blunder, dismissing the constant. Yet decades later, dark energy's discovery resurrected the concept. Turns out, Einstein might have been right for the wrong reason. His constant wasn't keeping the universe static, but it perfectly described the accelerating expansion we observe today. The mechanics are mind-bending. While gravity weakens with distance, a planet's pull fades the farther you drift. Dark energy's push intensifies as space grows. Picture stretching a rubber band with dots on it. As the band expands, the dots move apart, but dark energy ensures that with each stretch, the next one happens even faster. This exponential effect explains why distant galaxies recede from us at ever-increasing speeds, their light redshifted into oblivion. What's truly unsettling is the scale of dark energy's dominance. In the early universe, matter's gravity held sway, slowing expansion. But as galaxies spread out, dark energy's influence grew. Roughly 5 billion years ago, it tipped the balance. Now, it accounts for nearly 70% of the universe's energy budget. If this acceleration continues, distant galaxies will eventually vanish beyond an unreachable horizon, leaving future astronomers with a sky nearly empty of stars. Yet mysteries linger. Why does dark energy's strength precisely match the critical density needed for cosmic expansion? Some theories suggest it's not constant at all, but a dynamic field slowly evolving like an invisible fifth force. Others propose it's the energy of the vacuum itself, quantum fluctuations in empty space generating a repulsive push. Whatever the answer, dark energy has rewritten cosmic destiny, ensuring the universe's fate isn't a fiery collapse or a slow fade, but a relentless, icy dispersal, a finale where even the fabric of reality may one day tear apart. What if dark energy isn't just a steady force pushing the universe apart, but something far more sinister, growing stronger over time? This nightmare scenario, known as the phantom energy hypothesis, suggests dark energy's density might not stay constant but could increase as space expands, accelerating the universe's demise to unfathomable extremes. Picture a rubber band stretched tighter and tighter until it snaps. Now replace the rubber band with the very fabric of reality, and you've got the Big Rip, a cosmic doomsday where galaxies, stars, and even atoms are torn apart by dark energy's escalating grip. The math behind this is as chilling as it is elegant. In most models, dark energy's push stays constant, a fixed property of space itself, but phantom energy defies that stability. Its repulsive force grows as the universe expands, creating a feedback loop where more stretching leads to more dark energy, which leads to even faster stretching. If this continues, the acceleration wouldn't just carry galaxies away. It would overpower gravity, electromagnetism, even the nuclear forces holding atoms together. First, galaxy clusters would vanish over the cosmic horizon, isolated islands drifting into darkness. Then, individual galaxies would unravel, stars ripped from their orbits. In the final moments, planets, molecules, and eventually atoms themselves would be shredded apart, leaving behind a desolate, empty universe where not even light could escape the void. The timeline for this apocalypse depends on how quickly phantom energy gains strength. Some estimates suggest it could happen in as little as 22 billion years, a blink of an eye on cosmic scales. Others argue the process might take far longer, leaving civilizations of the distant future with a slow-motion front-row seat to the end of everything. But here's the twist: we don't yet know if phantom energy is real. Current observations fit both constant dark energy and phantom energy models, like trying to tell if a car's engine is idling or quietly accelerating just by listening to the hum. This uncertainty fuels some of cosmology's most urgent questions. Could phantom energy's fingerprints be hiding in subtle changes to the cosmic microwave background? Might future telescopes detect ghostly variations in how supernovae fade, hinting at dark energy's evolving nature? For now, the Big Rip remains a haunting possibility, one that reminds us how much we still don't understand about the forces shaping existence. And whether the universe ends in ice, fire, or a phantom's grip, one thing is certain: the answer lies in the dark. Scientists hunting for dark matter face a unique challenge. They're searching for something that refuses to interact with almost everything else in the universe. But if dark matter is real, it must be made of something, and the leading candidates sound like they're ripped straight from a sci-fi novel. At the top of the list, WIMP, weakly interacting massive particles. These hypothetical heavyweights could be 10 to 100 times the mass of a proton, drifting through space like cosmic ghosts. Despite their heft, WIMP barely acknowledge ordinary matter, passing through it billions of times a second without a whisper. Yet, if they exist, there's a tiny chance, about 1 in a quadrillion, that a WIMP might bump into an atomic nucleus, sending a faint signal physicists could detect. That's where experiments like XENO-NNT come in. Nestled deep beneath Italy's Gran Sasso mountain, shielded from cosmic rays by a mile of rock, this ultra-sensitive detector holds a vat of liquid xenon. If a WIMP collides with a xenon atom, it should produce a flicker of light and a burst of electrons, a signature scientists have spent decades chasing. Similar detectors, like LUX Zeppelin in South Dakota and Panda X in China, operate like high-stakes fishing nets, waiting for that elusive dark matter bite. But WIMP aren't the only game in town. Enter action's ultra-lightweight particles, theorized to solve a puzzle in quantum physics. Unlike WIMP, actions would be trillions of times lighter, behaving less like stealthy boulders and more like a cosmic fog. Despite their minuscule size, actions could convert into photons in the presence of strong magnetic fields, a quirk experiments like ADMX in Washington exploit. Picture a radio tuned to the universe's quietest station, listening for the faint static of actions turning into microwaves. Then there's the dark photon, a hypothetical particle acting as a bridge between dark matter and ordinary forces. Experiments at CERN Large Hadron Collider are smashing protons together at near light speed, hoping to conjure these shadowy messengers from the energy of collisions. It's like recreating the conditions of the early universe in a 17-mile underground loop, searching for a needle in a haystack made of other, stranger needles. But the lack of definitive detections has led some to rethink the rules. Could dark matter be fuzzy, made of wave-like particles spread across light years? Or sterile neutrinos, elusive cousins to the nearly massless particles zipping through supernova? Some theories even suggest dark matter isn't a single thing but a mix of particles, each leaving different cosmic fingerprints. Every null result narrows the hunt, ruling out possibilities like a detective crossing suspects off a list. The absence of WIMP in underground labs has pushed physicists to consider lighter, weirder alternatives. The silence of action detectors hints they might be rarer or quieter than predicted. Yet with each dead end, the puzzle grows richer, reminding us that dark matter's true nature might be wilder than we've dared to imagine. Until then, the experiments continue, listening for the universe's quietest secrets in the deepest shadows. The cosmic microwave background is like a fossilized whisper from the universe's infancy, a faint glow from when the cosmos was just 380,000 years old. Today, it fills the sky in every direction, a near-uniform sea of microwave radiation. But hidden within this seemingly featureless fog are tiny temperature variations, imprints of the earliest density fluctuations that would one day grow into galaxies, clusters, and the vast cosmic web. What makes these variations truly mind-blowing? They're the universe's way of revealing dark matter's hidden hand in shaping everything. The Planck satellite, a European Space Agency mission, spent years mapping these subtle temperature differences with staggering precision. Imagine taking a photo of a newborn baby and seeing, in the wrinkles of its skin, the exact blueprint for the adult it would become. That's what Planck did for the cosmos. The hotter and cooler patches in the CMB, some just 1 part in 100,000, correspond to regions where matter was slightly denser or sparser. But here's the catch: ordinary matter alone couldn't have created these patterns. The gravitational pull needed to sculpt them required something far more massive, something invisible. Dark matter's role becomes clear when you follow the math. The CMB's fluctuations act like a cosmic speedometer, revealing how fast sound waves traveled through the primordial plasma. Ordinary matter, protons and electrons, was constantly buffeted by radiation pressure, creating a push and pull effect that left distinct peaks in the data. But dark matter, unaffected by light, provided the gravitational anchor that amplified these ripples. Without it, the peaks would look weaker, smoother, fundamentally different. Planck's measurements matched predictions only when dark matter made up 27% of the universe's content, a number that lines up perfectly with galactic rotation curves and large-scale structure surveys. The real clincher, the CMB lets us peer into dark matter's behavior like no other tool. Some theories suggest dark matter might interact with itself or decay over time, leaving subtle scars in the microwave background. Planck found no evidence for this, supporting the cold, collisionless model where dark matter particles drift freely, shaping the universe with gravity alone. Other exotic ideas, like primordial black holes or warm dark matter, would have left sharper or fainter imprints in the CMB. Yet the data fits the simplest explanation: a universe where dark matter is an inert, slow-moving sea of undiscovered particles. Perhaps most astonishing is how these ancient photons constrain modern theories. Alternative gravity models like MUND struggle to explain the CMB's precise fluctuation patterns without invoking dark matter. Even the exact ratio of dark matter to ordinary matter critical for galaxy formation is etched into the microwave sky. The CMB doesn't just hint at dark matter's existence, it tells us how much there is, how it behaved in the early universe, and how it set the stage for everything that followed. Decoding this celestial blueprint required instruments of extraordinary sensitivity. Planck's detectors operated just a fraction of a degree above absolute zero, filtering cosmic noise from galactic dust, radio interference, even the glow of the Milky Way. The result, a map so detailed it revealed not just the universe's composition, but its age, shape, and ultimate fate, all woven into the fabric of those microwave whispers. And as future telescopes probe even finer details, the CMB may yet unveil dark matter's true nature, written in the faintest ripples of creation. To understand why dark energy behaves so bizarrely, physicists use a deceptively simple number, W, the equation of state. This parameter measures dark energy's pressure to density ratio, essentially, how much it pushes versus how much it weighs. For dark energy, W is tantalizingly close to -1, a value that transforms empty space into an engine of cosmic acceleration. Picture blowing up a balloon, but instead of your breath doing the work, the rubber itself generates an endless outward push. That's space under dark energy's influence. The more it expands, the more it wants to expand. This bizarre anti-gravity effect traces back to Einstein's cosmological constant, a term he originally inserted and later discarded in his equations of general relativity. A cosmological constant implies W equals exactly -1, suggesting dark energy isn't a substance but an inherent property of the vacuum, like a tax the universe pays just for existing. Quantum theory hints at why even empty space isn't truly empty. Particle-antiparticle pairs flicker in and out of existence, and their fleeting energy might be the source of this relentless push. Yet not all observations fit neatly into this box. Some data suggests W might deviate slightly from -1, hinting that dark energy isn't perfectly constant but could evolve over time. This is where projects like the Dark Energy Spectroscopic Instrument, or DAISY, come in. Mounted atop a telescope in Arizona, DAISY is mapping tens of millions of galaxies, quasars, and stellar explosions, measuring how cosmic expansion has changed across billions of years. By tracking how galaxy clusters grow, or fail to grow under dark energy's pressure, DAISY could reveal whether W has drifted, suggesting dark energy is more dynamic than we thought. The stakes couldn't be higher. If W isn't exactly -1, our entire understanding of cosmic fate shifts. A value slightly less than -1 could signal phantom energy, dooming the universe to a big rip. A value greater might mean dark energy weakens over time, allowing gravity to eventually regain control. Right now, the data points to a universe where W hovers stubbornly near -1, but the margin of error leaves room for whispers of something stranger. Every decimal place matters. The difference between W equaling -0.99 and -1.01 could decide whether the cosmos ends in ice, fire, or something beyond our current physics. And as DAISY and future experiments tighten their grip on this elusive number, we're not just refining a parameter, we're reading the universe's expiration date, written in the invisible ink of dark energy. Deep in the cosmic hinterlands, far from the bright lights of spiral galaxies like our Milky Way, lurk strange, ghostly islands, the dwarf galaxies. These cosmic minnows, some containing just a few thousand stars, shouldn't be able to hold themselves together. And yet, they persist, defying gravity's expectations with a secret weapon, an almost unimaginable dominance of dark matter. Take the Draco Dwarf, a faint smudge of stars orbiting the Milky Way. At first glance, it's unremarkable, just a wisp of light against the black, but peer closer and the truth emerges. Up to 99% of Draco's mass is invisible, a staggering ratio that makes it more shadow than substance. This disparity reveals dark matter's power in its purest form. In large galaxies, ordinary matter, stars, gas, dust, can mask dark matter's influence like noise drowning out a faint signal. But dwarf galaxies are so sparse, their visible components so meager, that dark matter's gravitational grip becomes unmistakable. Stars in these tiny systems whip around at velocities that would send them flying into the void if only visible matter were holding them. Instead, they trace wild, looping orbits dancing to the tune of an unseen conductor. Yet this dark dominance poses its own puzzle. If dwarf galaxies are so saturated with dark matter, why don't we see more of them? Computer simulations of cosmic evolution programs that meticulously model the growth of structure from the Big Bang to today predict a universe teeming with thousands of dwarf galaxies around every large spiral like the Milky Way. Instead, we've found barely a few dozen. Scientists call this the missing satellites problem, and it's one of dark matter's most nagging inconsistencies. Some theories suggest the missing dwarfs are out there just too dim to detect, their stars scattered or snuffed out by eons of cosmic tides. Others propose that dark matter isn't as cold or collisionless as we think. Warm dark matter made of lighter, faster particles might suppress the formation of the tiniest dwarfs, leaving behind only the larger survivors we observe today. Then there's the wild card. What if some dwarfs are too dark, completely devoid of stars, leaving only naked clumps of shadow matter floating unseen? The search for answers is relentless. Telescopes like the Vera Rubin Observatory are scanning the skies for ultra-faint dwarfs, while simulations grow ever more sophisticated, probing dark matter's quirks. Every discovery or lack thereof reshapes the puzzle, because in these dim, forgotten corners of the cosmos, dark matter isn't just a supporting actor, it's the entire show. And the more we learn, the clearer it becomes. The universe's smallest galaxies might hold the biggest clues to its darkest secrets. What if dark matter doesn't exist at all, and we've simply misunderstood gravity? That's the radical proposition behind modified Newtonian dynamics, or MUND, a theory that rewrites the rules of gravity to explain cosmic oddities without invoking invisible matter. Instead of galaxies being held together by dark matter's unseen pull, MUND suggests gravity behaves differently at extreme scales, bending the laws Newton and Einstein gave us. Picture a car speeding down a highway. At low speeds, the engine obeys familiar mechanics, but past a certain threshold, hidden gears engage, altering its behavior without any extra fuel. MUND proposes something similar. When gravitational acceleration drops below a certain tiny threshold, the rules change. The idea emerged in the 1980s when physicist Mordechai Milgrom noticed a peculiar pattern in galactic rotation curves. Stars orbiting a galaxy's outskirts move far faster than Newton's laws predict, but their speeds weren't random. They followed a precise mathematical relationship tied to acceleration. MUND tweaked gravity's equations to fit this pattern, eliminating the need for dark matter in many cases. For spiral galaxies, it worked startlingly well, matching observed rotations without invoking invisible halos. Even some astrophysicists drawn to its elegance called it too beautiful to ignore. But beauty isn't proof, and MUND faces brutal challenges. The bullet cluster, where dark matter separated from visible matter during a collision, is a glaring example. MUND struggles to explain why gravity's pull in the cluster doesn't align with the glowing gas. If gravity were simply modified, the lensing effects, the bending of light from distant galaxies should follow the visible mass. Instead, they trace an invisible scaffold exactly as dark matter predicts. It's like watching a ballet where the dancers move as if tugged by strings no one can see. MUND proponents have proposed extensions like adding phantom dark matter fields, but these patches risk making the theory as convoluted as the problem it aimed to solve. Cosmic structure poses another hurdle. The early universe's density fluctuations, etched into the cosmic microwave background, require a gravitational anchor to grow into galaxies and clusters. Cold dark matter's sluggish particles fit this role perfectly, while MUND offers no natural substitute. Simulations of galaxy formation under MUND produce distributions that clash with observations, missing the intricate filamentary web dark matter effortlessly explains. Even mundane phenomena like the motions of galaxies within clusters often demand extra unseen mass, essentially forcing man to reinvent the dark matter it sought to banish. Yet the debate isn't settled. Some intriguing observations, like certain dwarf galaxies with orbits that align better with Mund predictions, keep the theory alive. Others point to subtle anomalies in spacecraft trajectories or the peculiar accelerations of wide binary stars as potential cracks in gravity's established laws. But until man can consistently explain all the evidence from colliding clusters to the universe's large-scale architecture, dark matter remains the reigning paradigm. The irony is profound. In trying to rid cosmology of invisible entities, man inadvertently highlights just how much the evidence demands them. Science thrives on such tension. Every unexplained wobble in a star's path, every anomaly in a galaxy's spin, invites us to question, are we missing a cosmic ingredient or misreading the recipe itself? For now, dark matter's explanatory power outweighs its rivals, but the hunt for alternatives ensures we never stop testing the boundaries of the known. After all, the universe owes us no obligation to conform to our intuitions. Whether the answer lies in modified gravity or hidden particles, the truth will be written in the motions of the stars. Dark energy might not be the unchanging force we once assumed. Recent observations hint that its repulsive power could vary across cosmic time, a possibility that would rewrite the universe's fate. When astronomers first discovered dark energy in 1998, they assumed its strength, represented by that critical equation of state parameter, W, was fixed at exactly -1, a constant push embedded in space itself. But as telescopes collect more data, anomalies emerge. Some supernova appear dimmer than expected, suggesting dark energy's grip wasn't always as firm as it is today. It's like discovering a car's cruise control has been subtly adjusting its speed all along, except here, the car is the entire cosmos, and the speed changes decide whether everything ends in ice, fire, or something stranger. The evidence lies in the universe's expansion history. By measuring distant supernova, the same cosmic mile markers that revealed dark energy's existence, scientists can track how fast space stretched at different epochs. Early analyses pointed to a steady acceleration, but newer studies revealed tantalizing wrinkles. The Dark Energy Survey, which catalogued thousands of supernova, found slight discrepancies in how brightness correlates with distance. If dark energy's strength were truly constant, these measurements should align perfectly. Instead, some data suggests W might drift, dipping below -1 in the past or fluctuating like a fading battery. The statistical significance is still marginal, what scientists cautiously call 2 sigma, meaning there's a 1 in 20 chance it's random noise, but the implications are seismic. Phantom energy, the most extreme variation, would mean dark energy grows denser as space expands, like a debt compounding interest until it's unpayable. In this scenario, the universe's acceleration isn't just steady, it's runaway, barreling toward a big rip where galaxies, stars, and atoms are torn apart. But there's a gentler possibility: quintessence, a dynamic field that ebbs and flows over billions of years. Unlike Einstein's static cosmological constant, quintessence could behave more like an invisible fluid, its pressure shifting as the universe ages. Some models even allow for W to oscillate, turning dark energy's push into a cosmic heartbeat, expansion surging and waning in epochs we haven't yet lived long enough to see. The debates rage because the stakes couldn't be higher. If dark energy varies, our entire cosmic timeline is up for revision. Was its strength different during the universe's fiery infancy? Could it have influenced galaxy formation in ways we've overlooked? Future instruments like the Vera Rubin Observatory and the Nancy Grace Roman Space Telescope aim to settle this by mapping billions of galaxies, probing deeper into the past than ever before. Each new supernova, each distant quasar, is a timestamp in dark energy's diary, and we've only read the first few pages. Skeptics argue these anomalies could stem from systematic errors, dust obscuring supernova, or biases in how we measure cosmic distances. Others propose dark energy isn't varying, but that our understanding of gravity is incomplete at interstellar scales. Yet the allure of a dynamic dark energy persists because it offers something rare in cosmology, a universe that's not just expanding but evolving. The next decade of observations will decide whether this is a fleeting statistical mirage or the first crack in our model of reality. And if the cracks widen, we might need to rethink not just the universe's future, but its very foundations. Among the wilder twists in the dark matter saga is the idea that it might not be made of discrete particles at all, but instead an ethereal quantum fog stretching across light years. This is the fuzzy dark matter hypothesis, where ultralight particles trillions of times lighter than electrons behave less like tiny bullets and more like sprawling waves, their quantum weirdness writ large across entire galaxies. Picture throwing a pebble into a pond, the ripples spread outward in delicate, overlapping rings. Now imagine those ripples light years wide, their gentle undulations sculpting the cosmos itself. The math behind this is as elegant as it is strange. If dark matter particles are incredibly light, say around 10 to the power of -22 electron volts, their quantum wavelengths could span thousands of light years, blurring the boundary between particle and wave. Unlike traditional cold dark matter, which clumps into dense halos, fuzzy dark matter's wave nature prevents it from packing too tightly, smoothing out small-scale structures. This could explain some nagging cosmic quirks, like why simulations of cold dark matter predict more dwarf galaxies around the Milky Way than we've observed. The wave's natural fuzziness might suppress the formation of these tiny galactic satellites, leaving behind only the larger ones we see today. The real magic happens in galaxy cores. Cold dark matter models often predict cuspy, dense centers in galaxies where invisible matter piles up steeply. Yet observations reveal many galaxies have fluffier cores, their dark matter distributions more spread out. A mismatch fuzzy dark matter neatly resolves. Those vast quantum waves resist bunching up too sharply, like a crowd of ghosts refusing to squeeze into a closet. The result, galactic cores that match telescope data without ad hoc fixes. Even the Milky Way's own dark matter halo might hum with these subtle wave rhythms, their peaks and troughs gently guiding stars along their orbits. But how do you test something so intangible? One clue lies in the cosmic web's finest threads. Fuzzy dark matter's waves should imprint a unique signature on the distribution of the universe's smallest structures, ultra-faint galaxies and diffuse gas filaments. Telescopes hunting for these wispy tendrils could spot the telltale gaps or spacing patterns left by quantum interference. Another avenue involves pulsars, the universe's precision clocks. As fuzzy dark matter's waves ripple through space, they'd subtly warp spacetime, causing pulsar signals to oscillate in predictable ways. It's like listening for the echo of a bell ringing across an invisible ocean. Critics argue the theory introduces its own puzzles. If dark matter is this light, why haven't we detected its particles yet? And can quantum effects really dominate on galactic scales? Yet fuzzy dark matter's allure is undeniable. It transforms the cosmos into a quantum canvas, where the rules of the infinitesimal govern the structure of the colossal. Whether it's the final answer or just another step toward the truth, one thing's clear: the universe's hidden depths are far stranger than we ever imagined. And somewhere in that quantum haze, the next great cosmic revelation might be waiting to wave back. Between the glittering superclusters and galaxies that thread the cosmos lie the voids, vast deserts of near-nothingness so enormous they defy comprehension. These cosmic dead zones, some spanning hundreds of millions of light years, aren't just empty. They're actively growing, stretched wider by dark energy's relentless push. Imagine blowing up a balloon with a handful of sequins glued to its surface. As the balloon inflates, the sequins representing galaxies drift apart, but the empty patches between them stretch even faster, becoming disproportionately large. That's the universe's void regions, where dark energy's antigravity overpowers gravity's feeble grip, accelerating expansion into overdrive. Inside a void, the density of matter can be less than 1/10 the cosmic average. A single void might contain a handful of dim, isolated galaxies, floating like lost ships in an ocean of darkness. The largest known, the Boötes void, spans 330 million light-years, a volume so empty that if our Milky Way sat at its center, we wouldn't have discovered the existence of other galaxies until the 1960s. What makes these regions so eerie isn't just the absence of stars, but the way they behave. While galaxy clusters cling together, resisting dark energies pull through sheer collective gravity, voids surrender completely. Their expansion isn't just faster, it's uneven, warping spacetime like taffy being pulled from all sides. This lopsided growth leaves forensic traces. As voids swell, they carve pressure waves into the cosmic microwave background, leaving cold spots in their wake, ghostly fingerprints on the universe's oldest light. Their boundaries also act like funhouse mirrors, subtly distorting the shapes of background galaxies through a phenomenon called integrated Sachs-Wolf effect. Dark energy's dominance here is so absolute that voids essentially serve as cosmic laboratories, offering a pristine view of its repulsive force without the messy interference of matter. Yet even emptiness has a lifespan. As dark energy's influence grows, voids will merge, their walls dissolving until the universe resembles a foamy sea of ever-expanding bubbles. Galaxies stranded in these regions will fade from view, their light stretched beyond detectability. Eventually, the voids themselves might evaporate, leaving behind a featureless, infinite dark, a future where dark energy's triumph is absolute. But for now, these haunting gaps remind us that the universe isn't just expanding, it's being rewritten one void at a time. In 2015, astronomers studying the Perseus galaxy cluster noticed an eerie glow, a faint X-ray signal at 3.5 kiloelectron-volts or keV with no obvious source. This ghostly flicker, spotted by the European Space Agency's XMM Newton telescope, sparked a wildfire of speculation. Could it be the first direct evidence of dark matter decaying before our eyes? Imagine stumbling upon a faded letter in an attic, its ink barely visible, hinting at a long-lost secret. That's what this X-ray line represented, a potential whisper from the invisible universe. The excitement centered on a hypothetical dark matter particle called the sterile neutrino. Unlike its ordinary cousins, this elusive particle wouldn't interact via the weak force, making it nearly undetectable except through one telltale act. If sterile neutrinos existed, they might occasionally decay into ordinary neutrinos and photons, with the latter emitting X-rays at that exact 3.5 keV energy. The Perseus cluster, along with observations of the Andromeda galaxy and the Milky Way center, seemed to harbor this enigmatic signal, aligning tantalizingly with theoretical predictions. It was as if the cosmos had left a breadcrumb trail and scientists were racing to follow it, yet the plot quickly thickened. Follow-up observations with NASA's Chandra X-ray telescope and Japan's Hitomi satellite failed to consistently detect the line. Hitomi, in particular, should have been exquisitely sensitive to such a signal, but it found nothing. Skeptics pointed to alternative explanations, like sulfur ions in hot cluster gas emitting at a similar energy, or instrumental artifacts mimicking the signal. The debate grew fierce, with some researchers arguing the original detection was statistical noise amplified by selective analysis. It's the scientific equivalent of hearing a faint melody in a noisy room. Was it a symphony or just random static? The mystery deepens when you consider the stakes. Confirming the 3.5 keV line would have been a crowning achievement, not just identifying dark matter's composition, but opening a window into particle physics beyond the standard model. Sterile neutrinos could explain not only dark matter, but also the peculiar masses of ordinary neutrinos, weaving together two of cosmology's greatest puzzles. Instead, the line remains in limbo, neither definitively confirmed nor entirely dismissed. Newer telescopes like ESA's upcoming Athena mission may finally settle the debate, scanning the X-ray sky with unprecedented precision. For now, the 3.5 keV signal embodies the razor's edge of dark matter research where hope and skepticism collide. Every flicker of data could be a breakthrough or a blind alley, reminding us how hard it is to study something that refuses to interact with the tools we've built. Whether this X-ray shadow fades into obscurity or emerges as a landmark discovery, it underscores a thrilling truth. The hunt for dark matter isn't just about filling gaps in our knowledge. It's about learning to see the universe in a light we've never used before. What if dark energy isn't some exotic force or vacuum energy, but a cosmic mirage, an illusion created by the universe hitting its information storage limit? This mind-bending possibility, known as holographic dark energy, emerges from the crossroads of quantum mechanics and general relativity, where space itself might be a projection of deeper, two-dimensional laws. Imagine the universe as a hard drive. If it can only hold so much data, the way it encodes reality could generate repulsive pressure at the edges, accelerating expansion not because of some mysterious substance, but because the cosmos is literally running out of pixel space. The theory builds on the holographic principle, an idea first proposed to solve black hole paradoxes. Just as a 3D hologram is encoded on a flat surface, the universe's entire content, stars, galaxies, even us, might be etched onto a distant two-dimensional boundary. This isn't just philosophy. Math suggests that the maximum information any region of space can contain scales with its surface area, not its volume. When applied to cosmology, this limit could manifest as dark energy, a resistance to packing more bits into spacetime, pushing the universe to expand faster to free up information capacity. It's like a cosmic version of your phone slowing down when storage is full, except here, the storage is reality itself. Holographic dark energy makes startlingly precise predictions. Unlike the cosmological constant, which assumes dark energy's density stays fixed, this model suggests it evolves as the universe's information budget tightens. Early on, when space was smaller, information density was low and expansion crawled. But as the cosmos grew, its surface area, and thus information limit, struggled to keep up, creating an emergent repulsive force. Recent measurements of supernova and galaxy clustering reveal subtle hints that dark energy's strength might indeed drift over time, nudging observations closer to holography's predictions. The coincidence is eerie. The math aligns almost perfectly with the observed acceleration rate, as if the universe is following a script written in quantum bits. Critics argue the theory's elegance doesn't equal proof. Why should information limits generate repulsion instead of just halting structure formation? And how does this square with quantum field theory's vacuum energy calculations? Yet for supporters, holographic dark energy sidesteps the fine-tuning problem plaguing other models. Why dark energy's density is absurdly tiny compared to theoretical predictions. Here, the value isn't arbitrary. It's set by the universe's age and size, a natural outcome of information physics. The hologram isn't just a metaphor. It might be the universe's operating system, glitching under its own data constraints. Future telescopes could test this by hunting for deviations in how dark energy's push varies across cosmic epochs. If holography is right, the acceleration rate should trace a specific curve tied to the universe's information horizon, a shadow signature waiting in the data. Until then, the theory stands as a daring reminder. the answers to cosmology's biggest mysteries might not lie in new particles or forces, but in the invisible code underlying reality itself. And if true, the cosmos isn't just expanding, it's rendering itself into existence, one pixel at a time. The story of dark matter begins in the universe's first chaotic moments, less than a microsecond after the Big Bang, when the cosmos was a seething plasma hotter than the core of a star. In that primordial forge, ordinary matter, the stuff of stars and planets, was just one thread in a tapestry of exotic particles, most of which vanished as the universe cooled. But dark matter, whatever it is, survived. How it endured depends entirely on its identity. For WIMP, the leading candidates, the process resembles a cosmic game of musical chairs. In the early universe's extreme heat, WIMP would have been created and annihilated in pairs, colliding with each other as frequently as photons in a spotlight. But as the cosmos expanded and cooled, their interactions grew rare. Suddenly, WIMP couldn't find partners to annihilate with, leaving a residual population frozen into existence, a relic density precisely matching what we observe today. This thermal freeze-out mechanism is so elegantly predictive that it's known as the WIMP miracle. Actions, on the other hand, tell a different origin story. These hypothetical particles emerged not from collisions but from a phase transition, a cosmic symmetry breaking akin to water crystallizing into ice. In the early universe's unimaginable heat, a field called the Peck-Quinn field held perfect symmetry. But as temperatures dropped, this field snapped into a new configuration, releasing energy that condensed into actions. Unlike WIMP, actions are non-thermal relics. Their abundance wasn't set by annihilation rates, but by the initial conditions of the universe itself. Picture a pot of boiling water left outside in winter. The steam doesn't gradually vanish, it freezes into frost all at once. Actions might have formed in a similar sudden crystallization, their mass and density imprinted by the exact moment this cosmic symmetry broke. The difference between these two origins isn't just academic, it's etched into the universe's structure. Thermal relics like WIMP, heavy and slow-moving, would have clumped early, sculpting the cosmos into the galaxy-filled web we see. Actions, being ultralight, would have behaved more like a quantum fog, their wave-like nature smoothing out small-scale fluctuations. This divergence leaves fingerprints. WIMP-dominated universes predict more dwarf galaxies and sharper galactic cores, while action models produce fluffier halos and sparser satellites. It's a cosmic tug-of-war between top-down and bottom-up structure formation, with dark matter's birth mechanism dictating which side wins. Experiments are closing in on these primordial clues. Deep underground, detectors hunt for WIMP's rare collisions, hoping to catch a whisper from the universe's first second. Meanwhile, action searchers exploit their predicted weak coupling to electromagnetism, using powerful magnets to coax them into revealing themselves as faint radio waves. Even the cosmic microwave background carries echoes of this epoch. The precise patterns of its temperature variations could betray whether dark matter froze out thermally or emerged from a phase transition. The stakes couldn't be higher. If WIMP exist, they'll validate a universe shaped by annihilation and freeze out, a cosmos where dark matter's density was forged in the fire of particle collisions. If actions are real, the story shifts to symmetry breaking and quantum fields, a narrative where dark matter's abundance was locked in by the universe's cooling geometry. Either way, the answer lies in the physics of the first microsecond, a time so remote we'll never visit it, yet whose echoes surround us in the dark matter halos of every galaxy. And when we finally unravel which tale is true, we won't just be solving a puzzle, we'll be reading the universe's opening lines. Of all the mysteries surrounding dark energy, none is more baffling to physicists than the coincidence problem. The staggering improbability that we exist at the precise cosmic moment when dark energy's density is comparable to the density of matter. To grasp how bizarre this is, consider the numbers. dark energy's measured energy density is around 10 to the power of negative 122 in Planck units, an unimaginably small figure. Yet here's the kicker: despite being so infinitesimal, its current value just happens to be on the same order of magnitude as the density of all the matter in the universe right now, in this fleeting slice of cosmic time. It's like tossing a dart at a target the size of a proton and hitting it once in the entire lifespan of the cosmos, only to realize the bullseye aligns perfectly with the exact millisecond you decided to throw. This timing seems suspiciously convenient, and scientists have wrestled with two broad explanations. The first leans on the anthropic principle, the idea that our very existence as observers filters the kinds of universes we can inhabit. In this view, dark energy couldn't be much stronger, or galaxies would never have formed, and life wouldn't have emerged to ponder the question. But it couldn't be much weaker either, or the universe would have collapsed back into a big crunch before intelligence evolved. We find ourselves in this Goldilocks zone not because the universe conspired to put us here, but because we couldn't observe a cosmos where the numbers didn't allow our existence. It's less a coincidence and more a cosmic selection effect, like a fish marveling that the ocean's depth perfectly matches its need for water. The second explanation ventures into speculative but thrilling territory, the multiverse. If our universe is just one bubble in an infinite froth of universes, each with randomly determined physical constants, then it's no surprise we find ourselves in one where dark energy's value permits galaxies, planets, and life. Most universes might have dark energy so strong it rips atoms apart instantly, or so weak it collapses before the first stars ignite. We're the winners of a cosmic lottery we didn't even know we entered. String theory even offers a mechanism for this, with its landscape of possible vacuum states, each representing a universe with different laws, but critics pounce on both ideas. The anthropic principle feels like a philosophical shrug, offering no way to test why dark energy's value is what it is. And the multiverse, while mathematically elegant, remains frustratingly untestable for now. Some theorists seek a third path, suggesting dark energy isn't constant but evolves dynamically, tied to the density of matter like a cosmic seesaw. These tracker field models propose dark energy's strength adjusts over time, only recently coinciding with matter's density. If true, the coincidence isn't luck, it's physics we haven't yet decoded. The deeper you dig, the more unsettling the puzzle becomes. Dark energy's density is absurdly small compared to theoretical predictions, off by a factor of 10 to the power of 120. Quantum field theory suggests empty space should seethe with energy, yet the observed value is almost zero. Why is there an unknown symmetry cancelling out contributions, or does the universe have a built-in cutoff we've missed? Every proposed solution peels back another layer, revealing how little we understand about the rules governing reality. Perhaps the most humbling takeaway is this: dark energy's coincidence problem isn't just a numerical quirk, it's a glaring signpost that our best theories are incomplete. Whether the answer lies in anthropic reasoning, unseen dimensions, or an entirely new framework, one thing's clear: the universe isn't just expanding. It's daring us to solve its deepest riddles. Deep within the Milky Way, hidden beneath the familiar swirl of stars and gas, astronomers might have stumbled upon something unexpected: a ghostly disk of dark matter, thinner and more structured than anyone predicted. This controversial claim stems from data collected by the Gaia spacecraft, which has mapped the positions and motions of over 1 billion stars with unprecedented precision. While most models assume dark matter forms a vast, fluffy halo around galaxies, a team analyzing Gaia's observations noticed peculiarities in stellar motions that hinted at an additional gravitational tug, one that could only come from a dense, pancake-like layer of dark matter nestled within the galactic plane. It's like discovering that the invisible elephant in the room isn't just looming overhead, it's standing right beside you, barely noticed until now. the evidence lies in subtle deviations in how stars orbit the galaxy's center. Just as planets obey Kepler's laws, stars farther from the Milky Way's core should move slower than those closer in. Yet Gaia revealed stars slightly speeding up or slowing down in ways that couldn't be explained by visible matter alone. When researchers ran simulations to account for these anomalies, they found the best fit required not just a diffuse halo but a concentrated disk of dark matter, perhaps only a few hundred light-years thick, lurking alongside the Milky Way's visible disk. The implications are staggering. If real, this structure could mean dark matter interacts with itself in ways we've never considered, clumping into configurations far more complex than the smooth, featureless clouds we've long assumed. But not everyone's convinced. Skeptics argue the stellar motions could stem from mundane sources, a passing dwarf galaxy's gravitational wake, or even asymmetries in the Milky Way's bar-like core. Others point out that Gaia's data, while revolutionary, still contains uncertainties, especially for stars obscured by dust in the galactic plane. The debate boils down to a cosmic Rorschach test. Are we seeing a genuine dark matter feature, or is our brain, or in this case our math, filling in patterns where none exist? The stakes are high. If the disk is real, it could revolutionize dark matter models, suggesting particles with properties that allow them to cool and settle into disks, much like ordinary gas. If it's an illusion, it's a reminder of how easily our assumptions about the invisible can lead us astray. Future observations may settle the score. Upcoming Gaia data releases will refine stellar trajectories, while telescopes like the Vera Rubin Observatory could spot faint, unseen structures tugging at the disk's edges. Until then, the Milky Way's potential dark disk remains a tantalizing, what-if, a shadowy layer to our galactic home, waiting to be confirmed or dismissed. Whether it's there or not, the controversy underscores a deeper truth. Even in our own cosmic backyard, dark matter continues to defy expectations, challenging us to rethink the unseen scaffolding of everything we know. If you could peer into empty space with a microscope powerful enough to see the quantum realm, you wouldn't find stillness, you'd witness chaos. Space itself is a seething foam of virtual particles flickering in and out of existence, a phenomenon physicists call quantum fluctuations. These fleeting ripples in the vacuum aren't just mathematical quirks, they carry real energy, and according to quantum field theory, that energy should be colossal. Here's where dark energy throws us a cosmic curveball. The vacuum energy predicted by quantum mechanics is a staggering 10 to the power of 120 times larger than the actual value we observe for dark energy. That's like calculating the weight of an ocean but measuring a single raindrop instead. This mind-boggling mismatch is known as the cosmological constant problem, and it's one of the most glaring unsolved puzzles in physics. The roots of this paradox trace back to Einstein's cosmological constant, a term he inserted into his equations to keep the universe static, then discarded when Hubble proved expansion. Decades later, dark energy revived the constant, but with a twist. Rather than balancing gravity, it represented the energy of empty space itself. Quantum mechanics seemed to provide a natural explanation. According to Heisenberg's uncertainty principle, empty space can't be truly empty. Particle-antiparticle pairs constantly pop into existence, borrowing energy from the vacuum before vanishing again. Summing up, all these fleeting fluctuations should generate an enormous zero-point energy, a background hum powerful enough to warp spacetime. But when astronomers measured dark energy's actual strength, it was almost zero compared to predictions, a discrepancy so vast it's been called the worst theoretical prediction in the history of science. Why does this matter? If quantum foam's energy were even a fraction of its predicted value, the universe would have torn itself apart nanoseconds after the Big Bang. Galaxies, stars, and life would have been impossible. Instead, dark energy's observed value is just strong enough to drive cosmic acceleration, but just weak enough to allow structure to form. This razor-thin balance raises two haunting possibilities. Either our understanding of quantum field theory is fundamentally flawed, or some undiscovered symmetry cancels out almost all, but not quite all, of vacuum energy's effects. Some theorists propose supersymmetry, a hypothetical framework where particles have shadow partners, could neutralize these quantum contributions. Others suggest the universe does contain that unfathomable vacuum energy, but it's locked away in extra dimensions or balanced by negative energy fields we've yet to detect. The most radical solution, dark energy, isn't vacuum energy at all, but something else entirely, a force or field that merely mimics the cosmological constant's effects. Quintessence, a dynamic energy field that evolves over time, could explain why dark energy's density aligns so eerily with matter's today without invoking quantum foam's absurdly large numbers. Alternatively, the holographic principle suggests spacetime's information storage limits might generate an effective dark energy, creating acceleration without any energy in the traditional sense. Whatever the answer, the cosmological constant problem underscores how little we grasp the universe's deepest rules. It's not just a math error, it's a clash between quantum mechanics and gravity, a signpost that our theories are incomplete. Solving it might require rewriting physics itself, bridging the gap between the infinitesimal and the cosmic. Until then, dark energy remains a mystery wrapped in a paradox, a whisper of vacuum energy so quiet it defies everything we thought we knew. Billions of years from now, the night sky will tell a chilling tale, one of vanishing stars, receding galaxies, and an ever-growing void. As dark energy's relentless push intensifies, distant galaxies will first dim, their light stretched into invisibility by the accelerating expansion of space. Then, one by one, even our closest cosmic neighbors will slip beyond an unreachable horizon, their light no longer fast enough to outpace the stretching fabric of reality. The local group, a tiny cluster of galaxies bound by gravity including Andromeda and our own Milky Way, may remain as an isolated island, huddled together in a sea of nothingness. But eventually, dark energy's grip will tighten even here. Given enough time, its repulsive force could overpower gravity's hold, tearing apart galaxies, solar systems, and even the fabric of atoms in a cataclysmic big rip. Picture a universe where every star, every planet, every molecule is alone in the dark, separated by distances so vast that not even light can bridge them. It's a future of ultimate isolation, a cosmos where the very concept of elsewhere ceases to exist. But this bleak trajectory isn't the only possible fate. Some theories suggest the universe operates in cycles, an endless cosmic heartbeat of expansion and contraction. In these scenarios, dark energy might eventually weaken, allowing gravity to reverse the expansion and pull everything back into a fiery Big Crunch. This singularity could then birth another Big Bang, resetting the cosmic clock in an eternal loop. String theory even offers a twist. Our universe might collide with others in a higher dimensional space, triggering a new inflationary epoch. These models turn dark energy into a temporary phase, a fleeting push before the pendulum swings back. Then there's the Big Bounce, a quantum alternative where the universe avoids total collapse. Instead of crushing into a point of infinite density, quantum effects could create a pressure so immense that space rebounds like a compressed spring, launching a new era of expansion. Dark energy's role here is murky. It might be the force that primes the bounce or a relic of the previous cycle. Either way, the universe becomes a phoenix perpetually rising from its own ashes. These competing visions highlight how little we truly know. Will dark energy's push grow stronger, dooming reality to icy disintegration? Or is its dominance a prelude to renewal, a single stanza in an infinite cosmic poem? The answer lies in the nature of dark energy itself, whether it's a constant force or something dynamic, evolving with time. Future observations of supernova, galaxy clusters, and the cosmic microwave background could tilt the scales toward one scenario or another. Until then, we're left with a humbling truth. The universe's grand finale is written in a language we've only begun to decipher, its final chapters hidden in the dark. From ghostly particles streaming through your body to the phantom energy that could one day tear reality apart, dark matter and dark energy aren't just cosmic footnotes, they're the hidden architects of existence. We've journeyed through 25 mind-blowing facts that rewrite everything we thought we knew. How galaxies spin faster than they should because of dark matter's invisible grip. How dark energy's repulsive force is stretching the universe toward an uncertain fate. And how the cosmic web's vast filaments guide galaxies into place like beads on an invisible string. We've seen the bullet cluster rip matter from its shadow, watched dwarf galaxies defy gravity with their dark dominance, and peered into voids so empty they reveal dark energy's accelerating push. Each discovery peels back another layer of the cosmos, reminding us that the universe isn't just stranger than we imagine, it's stranger than we can imagine. But here's the thrilling part, this story isn't finished. Every unexplained anomaly, the Milky Way's potential dark disk, the Eerie 3, 5 kV X-ray signal, the way dark energy's density defies quantum predictions, is an open invitation. Maybe the next breakthrough will come from a viewer watching right now. Maybe you'll be the one to crack the code, whether through a telescope, a particle detector, or a stroke of mathematical genius. Science isn't just about answers, it's about questions that propel us forward. So tell us in the comments which fact reshaped your view of the cosmos. Was it the chilling possibility of a big rip, or the way dark matter's tendrils sculpted the universe from the shadows? The cosmos is full of mysteries waiting to be unraveled, and this is just the beginning. If you're as captivated by these cosmic enigmas as we are, hit subscribe and join us as we keep exploring the universe's deepest secrets. Because the next time you look up at the night sky, remember, you're not just seeing stars. You're glimpsing the tip of an invisible iceberg, a reality far grander and more mysterious than meets the eye. And who knows, the greatest discoveries might still be hiding in the dark.